Hey everyone, this is the video solution for quiz number 5 from July 20th. Let's say, number 1. We have a helium nucleus. The charge on a helium nucleus is plus 2e, where e is the fundamental charge. Enters a magnetic field of strength 0.8 teslas at an angle of 45 degrees at a velocity of 100,000 meters per second. Okay. So let's sketch that just so you can get an idea of what's going on here. So let's draw our magnetic field going this way. Here's our magnetic field. And then in a different color, if I can find a different colored marker, no, that's too close to blue. Where's my brown marker? All right, I guess a red pen will do. All right, in the red pen, I will draw the trajectory of the helium nucleus. So here's our helium nucleus going through. Hope that's visible. It looks like it is. At an angle of 45 degrees with velocity v. And we want to find the magnitude of the magnetic force on this helium nucleus. Okay, so we know that the magnetic force is given by what's called the Lorentz force law. And that's QVB times the sine of theta. In this case, theta is 45 degrees, so we have to keep that sine factor on there. So let's substitute. We know that the charge of a helium nucleus is going to be plus 2e because it's got 2 protons in its nucleus, but there's no electrons to negate that. So we'll have a, let's see, 2 times 1.602 times 10 to the negative 19 coulombs. We have our velocity, which is 100,000 meters per second. Oops. We have our magnetic field. I see I've screwed up in terms of space. Try and squish that in. Times the sine of 45 degrees. So multiplying all that together, we should find that the force on the helium nucleus is 1.81 times 10 to the minus 14 newtons. Turns out it's a very small number. All right, that's number 1. All right, number 2. We'll talk about a little bit about mass spectrometers, which use magnetic fields to turn the paths of ions and particles into circles and measure their mass by the radius of the circle. So let's see. A particular mass spectrometer has a magnetic field of 0.250 teslas. There we go. There's our magnetic field. And we want to find the magnitude of acceleration a doubly ionized nitrogen atom will feel if it enters at a velocity of 1,000,000 meters per second. That sounds like a really fast speed, but that's a pretty common speed for a charged particle coming out of a particle accelerator or something. Perpendicular to the direction of the magnetic field. In other words, theta equals 90 degrees. And we know that the mass of a nitrogen-14 atom is 2.33 times 10 to the minus 26 kilograms. And we want to find the magnitude of acceleration it's going to feel. So we want to use, ultimately, Newton's second law. So that gives us ma equals QVB sine theta. Now I'm going to make one simple one simplification here. Theta is 90 degrees. Sine theta is 1. So I'm just going to ignore that there. We can deal without that. We can do without that. So now in this case, MA equals QVB. And now we want to solve for A. QVB over M. So let's plug in our numbers here. We've got Q, the charge on a doubly ionized nitrogen atom. So it's lost two electrons. So it has a positive 2e charge. Forgot to write that down before. So let's write that in there. 2 times 1.602 times 10 to the negative 19 coulombs. We know our velocity, which is 1,000,000 meters per second. We know our magnetic field, which is 0.250 teslas. And then finally, I give you the mass of a nitrogen-14 nucleus, which is tiny, 2.33 times 10 to the minus 26 kilograms. And then calculating everything out, find that the acceleration is really, really large. 3.44 times 10 to the 12 meters per second squared. All right, that's part A. Part B, we want to find the radius of the atom's atomic path. Or I'm sorry, the atom's circular path. Atomic path doesn't make any sense. How do we find that? Well, now we need to realize that in a constant uniform magnetic field, the trajectory that a charged particle will follow is a circle. And because it's moving in a circle, it's going to experience a centripetal force. So, since it's not accelerating, it's only constantly changing direction, we can write it down like this. The centripetal force is equal to the magnetic force on the particle. So in other words, centripetal force from General Physics 1, you should know, is mv squared over r. And we already found the magnetic force to be QVB. So what we want to do is we want to solve for r. So let's see, what can we do to solve for r? We need to drop a factor of v. Then we divide by Q and B, and we move that R up. So solving for R will give us R equals MV over QB. And this is actually one form of what's called the cyclotron equation, because this is actually how cyclotron particle accelerators work. You use a magnetic field to steer the trajectory of a charged particle into a semicircle, and then it's passed through a straight tunnel where it's accelerated by a constant electric field, and then into another semicircle where its path is bent back around and accelerated through a second straight portion with another constant electric field in it to change its speed but not its direction. So you apply to the particle alternating electric and magnetic fields, the electric field to speed up the particle and the magnetic field to keep it moving in a loop so you can keep speeding it up. Anyway, that's sort of beside the point. The important thing is we have an equation to find the radius of the circular path. So again, let's plug in what we know. We know that the mass of a nitrogen-14 nucleus is 2.33 times 10 to the minus 26 kilograms. We know its velocity, its tangential velocity in this case, is going to be 1.00 times 10 to the 6 meters per second. Remember, magnetic fields don't change the speed of a particle. They only change the trajectory. And then we divide by the charge on the nucleus, which is going to be 2 times 1.602 times 10 to the negative 19 coulombs, and by the magnetic field, 0.250 teslas. So calculating all that out, we find that the radius of the circular path that the atom will follow, or the nucleus will follow, is 0.290 meters. All right, that's number 2. All right, number 3. We have a rectangular coil of wire, 6 centimeters long and 2 centimeters wide. And it's carrying a current of 50 milliamps. Let's convert that into amps. That's going to be 0.0500 amps. This is going to be 0.0200 meters, and this is going to be 0.0600 meters. All right. So, if the coil has 200 loops of wire, what is its magnetic moment? All right. So the magnetic moment mu of a coil of n loops of wire is going to be n times the current going through it times the area of the loop. This is a rectangular loop. So in this case, we'll have n, then we'll have I, and then we'll have the length times width of the rectangle. So plugging stuff in, we have 200 turns of wire, or 200 loops. We have a current of 0.0500 amps going through the loop. Then we have a length of 0.0600 meters and a width of 0.0200 meters. So multiplying all that together, sorry, this is part A. We find that the magnetic moment of this current loop is going to be 0.0120 amp meters squared. Now for part B, what is the torque on the loop if we place it in a magnetic field of half a Tesla perpendicular to the coil? So let's look at the side view. Label this top view. Here's our side view. Here's our current carrying coil. Here is the magnetic field perpendicular to that current carrying coil. And the magnetic field has a strength of 0.5 Teslas. So the torque between the magnetic field, the torque between the magnetic field and the magnetic monopole is going to be, or the magnetic dipole moment is going to be mu b sine theta. Now, because it's perpendicular, theta equals 90. So sine theta is 1, so it's just going to be the magnetic moment times the magnetic field of the that's going through it. So multiplying this out, let's see, our magnetic moment is 0.0120 amp meters squared. Our magnetic field is 0.500 Teslas. So this is going to have a torque applied to it of 0.00600 Newton meters. And that's number 3. All right, number 4. We have a high voltage DC power line carrying a current of 240 amps. So here's our power line. Carrying 240 amps, and it's 20 meters above the ground. Forgive my art skills. I'm not a great artist. So I'll take those to be power lines. Or, I guess, telephone poles or something. Now we want to find, we know that a current carrying wire will generate a magnetic field. And we want to find what is the strength of the magnetic field at ground level if this current carrying wire is 20 meters above the ground. Well, we know from our experiment, we know from our calculations using Ampere's law, that the magnetic field of a current carrying wire is mu naught I over 2 pi r. So, let's see, what do we need to find out? Well, we already know current, we know distance, 20 meters, and mu naught and pi are just constants. So, let's plug everything in to calculate the value of the magnetic field. All right, so mu naught is a quantity called the vacuum permeability. And it represents the ability of empty space, or free space as it's sometimes called, to transmit a magnetic field. It's pretty analogous to the vacuum permittivity epsilon naught that showed up when we were talking about electrostatics. At any rate, mu naught is actually defined to be 4 pi times 10 to the minus 7 newtons per ampere squared. That seems like weird units. It's to make everything make our magnetic field turn out in units of Teslas given current in amps and distance in meters. All right, so there's our value for mu naught. We have our current, which is 240 amps. And then 2 pi r is just 2 pi times the distance that the ground is from the current carrying wire. So plugging everything in, we find that the magnetic field at ground level is going to be 2.40 times 10 to the minus 6 Teslas. It's pretty weak. Magnetic fields tend to be pretty weak in terms of Teslas. The Tesla is a large unit. But this is also quite a bit smaller than the magnetic field just due to the Earth. Usually the magnetic field due to the Earth at ground level is approximately half a Gauss, or 5/10,000ths of a Tesla. So this is like a factor of 20 smaller than that. So it turns out that the Earth's magnetic field is quite a bit stronger in ground level than the magnetic field due to even a power line carrying even a pretty large amount of current. All right, that's number 4. And that's the end of my solutions for quiz 5.